right, moving into section 3.5 on real zeros of polynomials. So we were looking in the previous section on doing some long division and some synthetic division in the idea of being able to solve polynomials that were either powers of 2, most of the time it was just powers of 3. And so what we're going to be able to do is now expand upon that and be able to solve other polynomials that may have higher powers. So, in the days before graphing technology was commonplace, mathematicians discovered a lot of clever tricks for determining the likely locations of zeros. And so the first thing that we're going to encounter on this Cauchy's bound is to determine an interval at which your zeros exist. And so we are going to start by defining what this bound is, by saying that if we're given a polynomial f of x equals, get a thinner line there, a sub n x to the n plus a sub n minus 1 x to the n minus 1 plus, and you keep doing this until we get down to a sub 2x squared plus a sub 1x plus a sub 0 with no x, which technically has kind of a power of 0, but we don't write that. So this is of the form polynomial. Basically, n would be the highest power. You could have it up to 10. You could have it 100. Whatever the case may be, I think the most that we get is about 4 or 5. Okay? Now, we are going to let m be the largest of the coefficients in absolute value. So, of all the numbers in front of the x's, we're going to take the biggest and not worry about the sign. The absolute value, that means it's always going to be positive. Then all the real zeros of our function f of x lie in this interval. And it is just an interval. And it's a bounded interval where we would take opposite of the m, which is the largest coefficient in absolute value, divide by, in absolute value, the leading coefficient a sub n. So a sub n is in front of your highest power here. Then we're going to subtract 1. Then, that's the left-hand bound, comma, we're going to do kind of the positive versions of these. So capital M divide by the absolute value of the leading coefficient plus 1. And that is referred to as Cauchy's bound. At which it narrows down the interval at which you have zeros, because there are infinite number of real numbers, and so in order for us to kind of narrow things down to solve which of these 4 numbers would make that equal to 0, which of these 4 numbers would make that equal to 0, it's going to be very hard out of an infinite amount of numbers to choose just 4 and figure out 4 that work. Alright, so we're going to determine the interval for which contains all real zeros in these 2 functions. So we have to know m, we have to know the leading coefficient. So remember, m is the largest of the coefficients in absolute value. So if I look along here, I'm just looking for the biggest number. I'm not even looking for the sign, I'm just looking for that guy right there, where m is going to equal 6 here. Now remember, a sub n is the leading coefficient. So my highest power, normally they're in descending order. They may try to trick you, so make sure you are in descending order, that we have 2 being that leading coefficient. So all we're going to do now is kind of plug those in to this interval. So we would have opposite of m over the absolute value of the leading coefficient. Well, it's already positive, so I'm just going to write that as 2, or you can do absolute value if it makes you feel better. Minus 1, comma, take that 6, divide by the absolute value of 2, plus 1. And then it's just simplifying that down. So simplify your fractions and then subtract or add each of those together. So we get 6 over 2, which actually is a 3, so I get negative 3 minus 1 on that one. And this becomes a positive 3 plus 1. Therefore, our interval looks like negative 4 to positive 4. Would be kind of the narrowed interval that we're looking for in this case. Okay? All right, let's look at the next example. Again, all we need to do to answer what this interval is identify the largest coefficient in absolute value and the leading coefficient. So, again, I'm looking along for these numbers in front of x, and don't forget the constant could be 1. That is one of the coefficients, and in this case, 12 is the biggest number. Therefore, 12 is going to be the m. And the leading coefficient, the highest power is right here, is an invisible 1. So I'm going to put a 1 there. And again, now I'm going to take each one of these, put them into this formula, and we get what follows. So it would be the opposite of 12 over the absolute value of 1 minus 1. And then we would end up getting 12 over the absolute value of 1 plus 1. And again, these are going to kick out our numbers. So 12 divided by the absolute value of 1 is just 12. But we have a minus in front, so I get a minus 12 minus 1. And then here, this becomes a 12 plus 1. Therefore, my final answer here comes from negative 13 to 13 is the narrowed interval in which we would have a 0. Okay? All right, very good. Now, adding along to this, we are now going to get another tool in our toolbox so that we can narrow the number of real roots that we have. Now remember, real numbers are kind of all those numbers that we know of so far. They can be positive, they can be negative, they can be fractions, decimals, whole numbers, irrational numbers. There's all kinds that it could be, okay? All right, so rational root theorem. We are going to learn what this gets us down to. So for some possibilities of rational roots of our polynomial. So we're going to start with that same polynomial. F of x is equal to a sub n x to the n plus a sub n minus 1 x to the n minus 1 plus, and it gets down to a sub 2x squared plus a sub 1x plus a sub 0. So that's kind of the polynomial of the form. A lot of times we like to see that in descending order, starting with the highest power. So given this polynomial with integer coefficients, if r is a rational 0 of our function f, then r is of the form plus or minus p over q. And that part right there is very important. R is equal to plus or minus p over q, where p is a factor of the constant term, which is just the number at the end, the a sub n, or not a sub n, excuse me, a sub 0. And q is a factor of the leading coefficient, which we just worked in above, a sub n. Okay? So we'll kind of do this by example, but when we ask for the possibilities of p's over q's, basically the p is coming from factors of this last number over the q's, which are the factors of your leading coefficients. You got to start at the back and come to the front. Now, this gives us a list of numbers to try in our synthetic division. So in the previous chapter, we looked at, okay, if 1 is a root, then we could synthetically divide that if it was like an x cubed, got us down to an x squared factoring polynomial, or one that we'd have to use the quadratic formula on, and we could solve for the other two roots. So this is much nicer, like I was saying before, than to start with something than to simply just guess. If none of those numbers in the list are zeros, then either the polynomials have no real zeros at all, or all the real zeros are irrational numbers. Okay? So here we're just going to use the rational root theorem to decide what are the list of possible rational zeros for our function. All right, in order to do that, remember, p comes from the factors of this constant. Q's come from the factors of the leading coefficient. So our ultimate answer is going to come from taking p's over q's. So let's just talk about factors of the p's. So p, factors of 3, since it's a prime number, are only 1 and 3. Coming from the leading coefficient, a sub n, I need factors. What do I multiply to get 2? Well, the only two things are 1 and 2. Remember, 2 is the only prime number that we have there, okay? Now, in order to get our list of possible rational roots, we now have to take each one of these factors and kind of match them together with our p's over q's. Now, I didn't worry about the signs here. This one was negative, this one was positive. And the reason being is because the list of possible rational roots ends up having plus or minuses in front of them. So you could get a positive version of that or a negative version of that. So here's where I usually just write the plus or minus p's over q's, okay? Each one of these is going to have a plus or minus in front of it. So I start with one of those, and I match that with the other ones in the Q. So if you start with this factor of P, we need to match that with this factor of Q and that factor of Q. So we're doing P over Q. So a 1 over a 1. 1 over 1, comma, to 1 over 2. So I get plus or minus 1 over 2. Then I take the other factor, now that I've depleted all the possibilities there with the 1, then I take the other factor and I match it with P's over Q's of each of the ones down below. So I would do 3 over 1, so I get plus or minus 3 over 1, and plus or minus 3 over 2. And here is my entire list. Now, we can simplify this a little bit, and this one as well. So we could say that it was plus or minus 1, plus or minus 1/2, plus or minus 3, and plus or minus 3/2 would be my possible rational roots. Now, do you have to write this and then simplify? Well, I would prefer this as your answer. If you can do this answer without writing it down and go ahead and simplify as 1 and 3, I'm perfectly okay with that. Okay? All right, so let's look at the next one. The next one ends up having, again, for our rational roots, all we need are factors of the constant and factors of the leading coefficient. So this is where the P factors are going to come from, and this is where the Q factors are going to come from. Again, who cares about the signs? We don't care about that. So P has 20 as the constant. So I need to look at what numbers do I multiply to get 20. Well, in this case, I have 1 and 20. Then I have 2 and 10. Then I have 4 and 5. And those are all my possibilities for factors of P, which is the constant term. Now I turn to the leading coefficient, which is 2. Well, we just talked about factors of 2. They are only 1 and 2. So now when I go to the idea of taking P's over Q's, I need to now match all of these with both of these. So let's start with 1. Let's go 1 over 1. Well, that is just 1, so I get plus or minus 1. Let's go 1 over 2. That gives me plus or minus 1 over 2, which is 1/2. Now, let's turn to 2. Let's take 2 over 1, which gives me plus or minus 2. And let's do 2 over 2. Well, 2 over 2 is 1, and I already have that in my list, so no need to write it again. Let's now move to 4. Let's go 4 over 1, which gives me plus or minus 4. I would then do 4 over 2, which gives me a 2, and I already have it in my list. So let's move on to the next factor, which is 5. Do 5 over 1, gives me plus or minus 5. And 5 over 2, I don't have that in my list so far, so I'm going to do plus or minus 5/2. Moving on to 10, grouping 10 with 1. 10 over 1 gives me plus or minus 10. But when I do 10 over 2, 10 divided by 2 is 5, so I already have that possibility. And the last ones become 20 over 1, which gives me plus or minus 20. But then 20 over 2 gives me a 10, which I already have in my list. So this has now exhausted all the possibilities with my P's over Q's. Now you might say, man, that is a whole lot of numbers. Well, compared to infinity, that's not too many, okay? So here's a good way to know which of these could be a possibility within that, okay? So you'll have some exercises to do both, that Cauchy's bound and to find out possible rational roots using your P's over Q's. Some books use H over K's. This book ends up using P's over Q's. So now let's take these two tools along with our factor theorem that we used in section 3-4 to solve the following polynomials. Remember that we are looking for all the solutions which make the equation equal to 0. These are actually the x-intercepts of our function, okay? All right, so let's try this. We're going to do Cauchy's bound, we're going to do the rational root theorem, and then we're going to take those possibilities, see if they're in that bound, and if they are, we're going to try to use our factor theorem to see if we can determine any of those rational roots, okay? All right, so let's first do Cauchy's bound. Cauchy's bound was that m and that a sub n. So m was the largest coefficient in absolute value, which is that 5. A sub n is the leading coefficient, which is that 1 in front. So we take the opposite of m over the absolute value of that, which is 1, minus 1, and then we take the positive m over the absolute value of that, which is 1 plus 1. So if you work that out, we get negative 5 minus 1, which is negative 6. And this becomes 5 plus 1, which is 6. So the Cauchy's bound says that all of those zeros for this polynomial have to lie between negative 6 and 6. Now, let's use our rational root theorem. So that's part of it. Now, let's do rational root theorem, which is just what we did with our p's over q's. So p is going to come from the 3. Q is going to come from that 1 out front. So factors of Q, well, what do I multiply to get 3? It is just 1 and 3. With the 1 out front, that's very nice because what do you multiply to get 1? Well, it's 1 and 1. So we only have to write it once. So let's figure out what are our P's over Q's. Well, here we go. We're going to match this factor with everything down here where there's only 1. So plus or minus 1, and 3 we need to match with 1 plus or minus 3. These are our possibilities. Okay, so that's everything that we just learned in this section. But what can we now do from section 3-4? We can take these possibilities. So I'm going to start with positive 1. And I'm going to take all these coefficients from our polynomial, making sure we don't miss any terms. 3, 2, 1, nothing. That's good. And I'm going to divide that out synthetically to determine if this is a factor of this polynomial. Now remember, if it's a factor, we're going to get a remainder of 0. And if we have a remainder of 0, we can now take from this x cubed term, this would end up being an x squared, and we can either factor or use quadratic formula to find the other 2 roots. So let's bring our 1 straight down. Multiply by c, put it here, gives me a 1. Add gives me a 2. Multiply gives me a 2. Add gives me negative 3. When I multiply by 1 gives me negative 3. And looky there, on our first try I get that remainder of 0, which is good. Because remember, this becomes x cubed, that's what we started with. And when I divide it once, this now becomes an x squared. So this polynomial gets extracted to be x squared, plus 2x. Erase that. X squared plus 2x. Minus 3. From right here, these coefficients come down, and that gives me my new x squared polynomial. So I'm dividing it down. Now, the question would be, can I factor that? That's the easiest way to find those other 2 answers, those other 2 x-intercepts, those other 2 zeros. And so I'm going to try to factor that. Nothing in common, but I can break that trinomial down to 2 binomials. The last sign is a minus. They are different inside. I can split up my x squared as an x and an x. And can I multiply something to get 3 that I subtract to get 2? Absolutely. If I take 3 minus 1, I do get 2. Now remember, I need a positive 2. So I need a positive 3 and a minus 1. Now, here's the time that we go one step further. What makes that 0? Well, negative 3 makes that 0. What makes this 0? And that is positive 1. Now, we can't forget about this root that I started with, because that actually was a root as well. So I'm going to write it twice just so that you see that there are the 3 answers that make that 0 with that power of 3. But I will tell you that you probably just need to write both of them, because if it is repeated, normally it is not written twice in just a list. Okay? All right, very good. So kind of hopefully molding some of these things together that we're learning in the idea of solving polynomials, okay, which is important when doing some graphing stuff. So let's do the exact same thing with this polynomial. Let's start with Cauchy's bound, where I need m and a sub n. So m is the highest number here. That is a 10. A sub n is that leading coefficient, which is 4. So our interval becomes a minus to your 10 over 4 minus 1. And then I end up doing 10 over the absolute value of that, which is 4 plus 1. So when you do that, this becomes a negative 5 halves minus 1. So a negative 5 halves minus 2 halves is actually a negative 7 halves. And 5 halves plus 2 halves, gives you a positive 7 halves. So I get negative 7 halves to positive 7 halves as the bound where my answers are going to occur, where those zeros are going to occur. Okay? All right, now let's do our rational root theorem, where I have to look at the possibilities of each one of these factors with my p's over q's. Okay, so here's our rational root theorem. I need factors of p, which in this case is 2. So 1 times 2 are the only numbers that get 2 for me as whole numbers. And what are the factors of 4? Well, that's a little bit more because I get 1 and 4, but also 2 and 2. So if it's a multiple, then we don't write it twice. We just write it once. Okay? Now, our p's over q's, we have to now figure out what are all of these possibilities. So I'm going to start with 1 over 1. Then I'm going to start with 1 over 2. And 1 over 4. Each one of those with a plus or minus. So plus or minus 1, plus or minus 1/2, plus or minus 1/4. So those are the only choices that I have with 1 over 1, 1 over 2, and 1 over 4. Now I turn to the 2, and I do that with each one of them. So let's go 2 over 1, which is 2. I don't have that, so let's add it. 2 over 2 gives me a 1, which I already have. And 2 over 4, if I reduce 2 over 4, that gives me 1/2, which I already have as well. So this actually becomes the entire list of possible rational roots for our function. Now, I will recommend, this one just so happened that we ended up getting the first root on the first try. If you don't, then you have to continue with the possibilities to see whether or not you get a root of that equation, okay? So let's start with positive 1. And I'm going to take this cubit along with its coefficients of 4, negative 10, negative 2, and 2. And I'm going to synthetically divide by bringing the 4 down, multiplying, adding. Multiply by 1 gives me negative 6. Add is negative 8. Multiply by 1 gives me negative 8. Add gives me a negative 6 because that is not 0. 1 is not a real root or a rational root of that. So if 1 didn't work, let's go to the next one. Let's try negative 1. 4, negative 10, negative 2, 2. That doesn't change. I bring my 4 straight down, and I multiply, gives me negative 4. When I add, I get negative 14. Multiply, I get positive 14. Add, I get 12, excuse me. Multiply gives me negative 12. And when I add, these two gives me negative 10. Again, I'm looking for a 0 to make that a root. So that doesn't work. Means that neither one of those works. Okay, so now let's try a positive 1/2. Still sticking with 4, negative 10, negative 2, and 2. Don't forget any placeholders if you have a term missing. So I'm bringing my 4 straight down. Multiply by 1/2 gives me 2. Add gives me negative 8. Half of negative 8 is negative 4. Add is negative 6. Half of negative 6 is negative 3. When I add again, I get something other than 0. Now, keep persevering because there should be one that works. And if not, which I'm not going to give you any of those, then you don't have any rational roots, okay? But I will tell you in the problems that you will do, you will have a rational root. You just got to find it. All right, let's try negative 1/2 would be the next possibility. Bring the 4 down. Multiply half of 4 is 2, but negative times a positive is a negative 2. Add gives me negative 12. Negative 1/2 times a negative 12 gives me a positive 6. Add gives me 4. Negative 1/2 times 4 is a negative 2, and ding, 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 look right there. Woo-hoo, we found one of those rational roots to be negative 1/2. So negative 1/2 is one answer, but I'm still looking for 2 because remember, we end up having this power of 3 here. That tells me that I have 3 answers on that. All right, so now what do I have? Well, we're going to extract these numbers here into a quadratic that we can solve. Now the last one factored, but this one may not factor. So if this is x cubed, remember this is x squared. So I'm going to do that up here. I get 4x squared minus 12x plus 4 as my polynomial. I'm going to set that equal to 0 so that I can solve that. Now, our advantage to having equal to 0 is that notice I have numbers in common there. I have 4's in common with each one of those. So to make life easier, because you have an equals, you are allowed to divide everything by 4 and get a new equation of x squared minus 3x plus 1 equals 0. So it's much easier to factor something like this with a coefficient of 1 in front than it is to have all of those other larger numbers, okay? So if I try to think about factoring, this would end up having a negative negative because they are the same that match the first. But can I multiply anything to get 1 that I add to get 3? And in that case, the answer is no. So unfortunately, this cannot be factored. But if you remember the quadratic formula, you can now solve for the other two roots. So we need to do that. So here goes. X equals negative b plus or minus the square root of b squared minus 4ac all over 2a. If you have to sing it, please do so. All right, so here is b, negative 3, a is 1, and c is 1. So we get x equals negative of b. So the negative of negative 3 is a positive 3. Plus or minus the square root. If I square b, I get a positive 9. Always you get a positive if you square anything. Minus 4 times a times c. So each one of those are 1. All over 2a, which is 1. That's why it's so important to know this and be able to work with the quadratic formula. If you missed that, you probably want to go back and practice it some more. All right, so what we have to do now is simplify in here. We get 9 minus, well, 4 times 1 is 4. So 9 minus 4 is a 5. So I end up with 3 plus or minus the square root of 5 all over 2. And in this case, that doesn't break down with our radicals. Those would be my other two numbers that put with negative 1/2 would end up giving me my other two answers, okay? So if they want you to separate it, then remember that would be 3 plus root 5 all over 2, and then 3 minus root 5 all over 2, splitting up that plus or minus in the top. So these would be our final answers there. Okay, and try to leave it as exact answers. Don't worry about taking it into decimal form. That would not be needed. So that's what we have in section 3.5. We are actually now going to proceed and be able to solve even more polynomials in the next section, as long as we talk about complex numbers first. So we will do that in section 3.6. See you there. Until next time.